Okay, so good afternoon. Today we'll be having another module. It's all about writing and naming chemical formulas. This is a three-part module. So we'll start first with writing chemical formulas. So let's just pull that up. Okay. So in writing chemical formulas, you have to understand what chemical names are. So chemical names are usually, of course, the names of the elements that you have in the periodic table, and these are usually represented by their chemical symbols. Most of the time, the chemical symbols are the first letter of the element plus, of course, another letter. Sometimes you might see that, for example, in this case, silver, the it's supposed to be Si, but of course, Si is taken by silicon. Then we refer to another point of reference, which is the Latin names. That's why it's Ag, that stands for argentum, and so on and so forth. So gold, it's from the Latin aurum, copper from cuprum, etc., etc. But in naming them, uh, usually it's the first letter of the element's name, the smaller letter, and then unless there's another letter or symbol that is taken by another element in the periodic table. Okay, these are explained in this table. So confusing elements, symbols explained. So you can see here the element, and then the name of the element, where it's coming from. It could be the Latin name or the mineral that it came from. There's always a reference to. So you can just go through this table or diagram uh, for more information about why those elements have uh, different names as compared to the others. I mean, where their names were generated. So for formulas, they are represented in different ways. It could be using a molecular formula, structural formula. You have the ball and stick model, wherein your elements or your atoms are represented by balls, and of course sticks with their bondings. And then you have the space filling model. You can see this in other references. This can also be a way to represent a chemical formula. Well, you can also represent it as the atom itself. This is a water molecule wherein we have the hydrogen atoms and oxygen atom. You have one oxygen atom and two hydrogen atoms. Or you can also represent it this way. This is also a representation of a chemical formula, like the material itself that we're using. So these are different ways. In interpreting chemical formulas, it's very important to understand the numbers that you see on the different chemical formulas. You have the coefficient and the subscript. The coefficient normally just tells you the number of moles or molecules in the substance, and that is involved in the reaction. The subscript, on the other hand, the smaller number, usually at the end of each element, this would indicate the number of atoms of that element in that compound. So for interpretation, let's for example, this um, compound. So in this case, you have 2 Na2O. So that's 2 times 2. It means that there are 2 moles of this compound, and there are 2 atoms of sodium initially, but of course, since there's 2 moles, that becomes 4 atoms of sodium and 2 atoms of oxygen. So you can see it from here. Therefore, the total number of atoms in this compound is 6. Let's go to the other one. Okay, barium phosphate. So we have barium. We have 3 times 3 molecules. And then, for example, for phosphorus, you have 2 times 3, that's 6. And then oxygen, 4 times 2, 8 times 3, that's 24. So in total, if you count the number of atoms in this formula, you have 39 atoms. Remember that when you have the parenthesis or the grouping symbol, you must multiply the subscript uh, on the outside of the parenthesis to everything inside the parenthesis before you multiply to the coefficient, which is this one. Okay. Okay, in writing chemical formulas, you also need to understand what oxidation numbers are. The common term for oxidation numbers will be the valence electrons. And where do you see them? You usually see them in the periodic table. For some elements, you're very familiar already, and that relies on the groups they have in the periodic table. Let's pull up a periodic table so that you can see it. Okay, where is my periodic table? Oops, it's not. Where's my periodic table? Oh, there you go. So here you go. Usually, the groups would identify what valence electrons they have or what oxidation numbers they have. For example, for group 1, most of these elements or all of these elements have a valence electron or oxidation number of 1. And then for group 2, of course, that's 2 and so on and so forth. But of course, you don't have a group 11, group 12. You don't have oxidation numbers which are 12 or 11. Then you have to understand the octet rule. But you can just zoom your periodic table. Okay, let's take, for example, silicon. Oh, silicon is 4. That's an exception. Let's go to bromine. Okay, bromine here, you can see there, in the first orbital, there is 2, and then they have 8, 18, and 7. So it means bromine will have an oxidation number of 2. Later on, I will be taking, uh, of course, describing to you when the oxidation number becomes positive or negative. But for now, at least you know where to identify. Like in this case, bromine has 2. So there you go. Okay, let's close that. Leave. Okay. So let's go back to our PowerPoint. So in writing chemical formulas, again, you have to know excuse me, the columns. For metals, the oxidation number is usually the number of valence electrons it gives away. And then for non-metals, usually the number of valence electrons is 8. For the group 14, the oxidation number is either positive or negative 4 because most of the time group 14 are the ones with the semiconductors. Therefore, they just share. Most of them use covalent bonding. And for family 18 or group 18, the oxidation number is 0. So let's go further. How do we understand chemical formulas? So chemical formulas are always composed of a positive half and a negative half. For example, water. When you split water into two, of course, there's hydrogen and oxygen. One is positive and the other one is negative. Usually, the first one written is the positive half, and the second one is the negative half. So in this case, in water, hydrogen is the positive and oxygen is negative. It says there, the element with the positive oxidation number is always written first, and the negative will be written second. So in this case, H2O, H has a positive, you go to your periodic table, hydrogen has a positive 1 oxidation number, and oxygen has a negative 2 oxidation number. That's uh, that's always the pattern or the form. The first one always is positive, and the second one is always negative. And always remember that the total oxidation numbers in a compound must equal 0. Yes, for each compound that you see in a chemical formula or in a chemical equation, ideally each one should have a neutral charge. Therefore, the oxidation numbers of that compound should balance out and they should be equal 0. Okay, how do you do that? You add subscripts after a chemical symbol when needed to make the oxidation numbers total 0. For example, H2O, the reason, how do we know this? Let's check if it's 0. Of course, H is 2. And the valence electron of water is 1. So 1 times 2, that's positive 2. The valence electron of oxygen is 2, and that's negative. So positive 2 minus 2, the whole thing is 0. Therefore, this is neutral. So water is neutral. Likewise, for calcium and chlorine together, you have to make sure that this should have a neutral. oxidation number, the oxidation number should be 0. So what we can do is study it. That's calcium. There's actually an easier way wherein you just overlap and like go across. So CaCl, I don't think this is neutral because this is positive to a negative one. If I get the oxidation number of the whole compound, that's positive 1. So it's not 0, there's a charge. So what you do, it's Ca, you understand that's 2, and then that's negative 1. Oh, okay, that's 2 positive for oxidation. Therefore, you have to add Cl, and then that's 2. Because this is a negative, this is a 1 negative or negative 1. So 2 times negative 1, that's negative 2. That's positive. The whole thing is 0. That's neutral. So the proper way of writing calcium and chlorine together, that's CaCl2. Okay. Okay, the easiest way to think of writing chemical formulas is to use the oxidation number without the positive or negative of one element as a subscript of the other element. Okay, these are other examples: sodium chloride, sodium oxide. Here you go. What happens? This is negative 2 and positive 1. If you add them together, that becomes negative 1 charge for sodium oxide. So instead of doing that, we just put a subscript 2 to sodium and add oxygen. That's Na2O. Aluminum oxide and lead oxide. And more technicalities about this, we call a positively charged ion as cation and a negatively charged ion as anion. So when naming ionic compounds, usually the first one retains the name of the element and the second element changes in form. And most of the time you make the suffix IDE, like sodium and chlorine. It becomes sodium chloride. That's an IDE. Okay? But when the second element is attached to an oxygen, or there is oxygen in the second element, or in the second compound, then the suffixes, they become different. You can use ITE, ite, or ATE, ate. That depends on the compound. So these are the common ones. For common cations, you have this. And for common anions, you have this. As you can see here, oxide. And then this is attached to oxygen, that becomes a carbonate. Phosphorus attached to oxygen, that's a phosphate. So that's it for this one. So there are two more um, PowerPoints accompanying this. What I did was really try to shorten them so that they will be easier to watch and they'll be easier to upload. Okay, so for now that will be it, and please wait for the next one. Okay, bye.